My name is Hoang. It's a pleasure for me to be representing SINTEF today at this conference. I have to say that I'm not a geothermal energy guy, but my background is structural and material mechanics. But I've been working with geothermal drilling and well completion for 10 years plus. Every time I see this picture here, I see the hope for humankind. I see that this is okay. This is big potential for energy need for humankind. This is Mother Earth is so generous, she's willing to give us everything that we need. It's just tiny amount of energy of geothermal energy can be sufficient for Earth, for energy need for all of us for a couple of decades. But things that look at what we have be able to extract energy from the Earth so far is what we have done is just scratching on the surface. We did not manage to have access to this full potential of such unlimited energy sources. But why is that? Like when I look at this, how much effort and how much money we investing into space energy, trying to understand what is going outside, and in comparison with the little effort that we try to put into understanding the Earth and also trying to develop technology to extract the energy from the Earth, I was saying that I was asking why is this lacking of motivation, lacking of money, or is it more challenging to understand, to go deep into the Earth and understand ourselves, understand what is going on in our side. So this question I leave it to you as a takeaway message, but today I just want to share with you, discuss with you some challenges related to well integrity when we are working with super hot and hot geothermal applications and some possible solution. This is an outline of my presentations, short introduction to SINTEF and why we are doing high temperature geothermal in Norway, some concern for well integrated high temperature exposure and possible solutions before I try to wrap up with some perspective. As some of you may not know about SINTEF, SINTEF is one of the largest independent research organizations in Europe. So we have more than 2,000 employees. This is international company, so with more than 75 nationalities. So if some of you are willing to come to Norway to work, so just send up your application and CV. So SINTEF is working based on the direct project and direct contract with together with clients to help them to develop technology and solution that's needed for society. Our headquarters is based in Trondheim. We have a second office, biggest office in Oslo, and this is different small offices spreading over Norway, as you see in the map here. So I say that together with client, we are aiming to develop some technology for better society in different sectors: energy, construction, food, mobility. Mobility and different sector also. But at the end of the day, this is SDG goals and climate is at our hearts. So we care about client and we care about client, climates and environments. With respect to geothermal R&D at SINTEF, so it's started from, it's not that long, it's like 15 years ago. So it's instigated based on interest from Norwegian oil and gas industry, because we have a oil and gas industry track record. And together with them, we try to identify technology bottleneck and also, some opportunities to go in these geothermal markets for energy exploration, drilling, exploitation. And afterwards, over the course of the time, so we are moving forwards with different topics like EGS, ADS, offshore, super hot, geothermal energy with international partners, heat pump, heating and cooling, and also underground energy storage. So our mission also is to support industrial network to help them to develop relation and collaborative portfolio of a project, and this is why we identify some relevant funding scheme, not only national funding scheme, but also this is international like Horizon Europe project, in order to help them to realize this innovation and technology. So why high temperature energy in Norway? Even though this is we don't have potential for high temperature in Norway, this is what the low enthalpy resources that we have. But as I said, this is the knowledge is generic and geothermal is universal. So we want to go to share knowledge and contribute to our part to the global effort. So as many of us know that this is as deeper as we go. We have a hotter resources and we have a higher energy output, and this is higher energy output is helping to compensate the upon investment cost of geothermal energy and lower some kind of levelized cost of electricity. A simple calculation that some of colleagues showed this morning, that this the energy output from 3 wells 400 Celsius is sufficient. Is to be balanced. This quite equivalent to the energy output from 40 wells at 200 Celsius. Think about this is a space that we save. Think about this as the length of the footprint that we may save when we're going to toward the upper end of the high temperature application here. But as we know, this is together with high risk. We have high risk. So one of the risks that we share here, this is well integrity for high temperature exposure. This picture here, you see this is typical well construction for geothermal wells, which differ a little bit significantly from oil and gas constructions, in the sense that we have a slotted liner in the production zone, and also the casing, different casing is cemented from casing shoe to the surface, which is not the case for oil and gas well. And all the system here is quite rigid and is constrained by the cement around, And this is when we're operating this geothermal wells, the whole system is subjected to temperature cycling. When we're warming up the well for production, and we were cooling down the well for maintenance and workout, and the temperature, high temperature, is leading to a thermal stress. This is the biggest problems that we may see in this in high temperature application here. Not to mention that we have a nasty chemical composition from the producer fluid. We may have a corrosive environments. Not to mention also silica scaling and also some erosion problems that you may see in the well. Next challenge is that how we manage to have a good cementing job from the casing shoe to the up to surface, especially when we have this is quite a long well, like 2 kilometers or maybe 3 kilometers. This is quite a challenge. Last but not least, we are still lacking the design standard. This is something that we are still working on. This is mainly most of the geothermal wells is designed following API standards, and some of them is following New Zealand standard, but it's working up to 350 Celsius. Beyond that, we are still lacking some standard for that. This is very challenging problems. We don't know what to follow, and I can show you a little bit. This is the consequences of the problems that we are dealing with when we are working with outside the standard. Here you can see this is more than 50% of production wells in Iceland was reported with problems in one way or in another. So you can see there's some problems, mainly like a casing degradation due to wear corrosions. Casing is fractured due to tensile burst collapse, and most of them you can see this is casing is plugged due to the scaling and so on. This is quite an interesting mechanism when we're talking about the tensile fracture in the casing and couplings. You see that this is when we are heating up the well for production, right? So the casing is constrained and it's loaded beyond the elastic limits and go into plastic behaviors. And when we are cooling down the well, so the casing is trying to construct, but it's constrained by coupling, so this is high thermal stress. Tensile stress is developed in the casing, leading to potential fracture, tensile fracture in the weak points in the welds, like the couplings, or maybe some damage, like a wear or some corrosion part of the casing. Another interesting problems and mechanism is related to annular pressure buildup in the welds. We wish to have a good cementing job from the casing shoe to the surface, but this is not the case in all the welds. So we may expect to have also to have bad cementing job, bad cementing design, and leading to some water pocket if we have a lot of excess water in the cement. So we may have a water pocket in the cement, or maybe pore fluid in the cement after it's hardened. And think what happens if we are heating this structure here, and the water here has no way out to escape. It's a trap between the casing and casing annulus. This is similar situation if when we are as a pressure cooker at your home, in your home. So think about it, since you are putting the water in the pressure cooker, you close the lid, and so this is the closing the venting mechanism here, and you're heating this the pressure cooker. This is pressure in the cooker is increasing up to the point that it's exceeding the structure resistance. So it's gonna be catastrophic damage here. This is same way when we have water pocket in this in the casing annulus. So as you see, this is cement is have an impact on the casing, but also this is casing also have impact on the cement. So it's working like a couple. So if you see this is if a casing is expanding during the temperature and pressure, it tries to push the casing toward the formations. So if formation is so soft, so you may see the cement fail in tensions in such conditions, and if the formation is so stiff, so the cement may fail in compression. So it's by plastic formation, as you see here in the figures. Also, another case on the opposite, when the casing is contracting when we are cooling down the welds. So some debonding mechanism between the casing and cement may happen, so creating microannulus between the casing and cement. Or the defect of the cement also, and the casing can lead to catastrophic consequences like a gas migration into and also some blowout event that we have seen in the past. So motivated by these challenges, so we are gathering this consortium, international consortium in the Horizon Europe, which is called Compass, with ambition to solve, contribute to solve these challenges. Our consortium is motivated also by these global efforts to continue to go into deeper and also harder resources that our colleague Halliburton have shown this morning. This consortium has 10 international partners from Iceland, UK, Norway, France, Netherlands, and Italy also. So our objective is to develop some technology and solution to mitigate this what may happen in superhot geothermal wells, and to ensure the sustainable power production from such a well. Okay, as we see, this is thermal stress is one of the biggest issue in such applications. So we need to mitigate that somehow. We need to reduce the thermal stress when we are heating and cooling the wells. One of the possibilities we may use this quite advanced materials with lower thermal expansion, like a titanium alloys, but this is quite expensive. Alternatively, we may think about a structure with flexibility, so not a rigid and conventional system, but it is allowed the structure to expand a little bit and accommodate the thermal expansion when we're heating the wells. This is the idea behind this flexible coupling solution here. It was developed and patented by our partners, ISOC, in previous projects like Hieu Nguyen and EGS. So the principle of that is when we're heating the casing, the couplings will accommodate somehow somewhat the displacement in axial directions and close the gap here. So it's reduce the stress in the casing and also reduce the risk for casing failure and in tension, but also in collapse. This solution, flexible coupling solution, was designed to handle this axial direction thermal stress mitigation. But what about this other direction, like the radial directions? The casing can be expanding also in these directions. So this is the idea behind for flexible foam cements. So we are designing this solution to work hand in hand with flexible couplings to mitigate thermal stress in all directions, increasing this flexibility in axial direction, but also in radial directions. The foam cement, some of you may know, this can be created by injecting hydrogen gas when we are cementing to create some gas bubbles in the cement solution. So creating quite a good, many advantages for well integrity in comparison with conventional solution. We have low density, low Young modulus, high ductility, and high compressibility. So it's increasing significantly flexibility of casing system and also contribute to ensure well integrity of in such a high temperature application. So what about this annular pressure buildup problems? It would be naive for us to think this is we can have a good cementing job in all the cases. This is not possible. We need to take this risk. It's not possible to have that. We cannot avoid some pore fluid in the cement. We cannot avoid some water pocket in some cases. We need to take the risk. We need to design some mechanisms as to be able to vent this fluid in such situations. This is similar mechanism as a venting mechanism as a pressure cooker, as I showed you this, previously. So if the pressure in the fluid is approaching the casing collapse, it will allow opening of this relief mechanism here, and also this vent this fluid effectively and reduce the pressure buildup potential. But what about this corrosions? Corrosion also we see this is quite a big problems of that, right? And we may think it is to use quite advanced materials like nickel-based materials or titanium alloys, but this is also very expensive. Alternatively, we can use this cost-efficient carbon steel materials as a backing material. And so we are adding on top of that some very thin layer of cladding materials, high corrosion resistant materials. The problem is how can we effectively manufacture such cladding pipe? In the project here, we are looking this method, which is called extreme high-speed laser cladding, ELA. So this, in comparison with conventional cladding, this is very efficient. It can be 100 times faster than conventional laser cladding. This is with lower heat input needed, and also this is surface. The final surface quality is quite good. And what is special with this technology is that you can, manufacture clad pipe with quite a small pipe, and also we can make it like quite a long pipe section, like 10 meters and 12 meters, as required for the casing systems. It was developed by our partner Hornes in Netherlands, but also is investigated and tested by partners in TWI in UK. But also we need also to have some understanding of material behavior with respect to how materials behave at high temperature. So we have done a lot of tests up to 500 Celsius to see this how is it function, not only casing cement, but casing material, but also cement materials. We need to have a sufficient understanding of durability of materials to see how the long-term exposure at high temperature, how that will affect on the mechanical properties of materials, and we need to test also this to how this verified how this is the full system is working, casing and cement together in a small scale before we are putting down in the pilot in the wells. All of that R&D and research development need to be performed before we are making sure that our solution is good enough to be used in the real well. But also we need to have a better understanding of the whole physics in the hot wells. There are many ways that we can achieve that. We can monitor the wells, we can monitor the wells, but it's quite extensive and quite expensive. So alternatively, we can develop we are developing also the simulation tools. It's similar as John's, and John is showing, but this John is developing some reservoir modeling, and here this tool here is developing to see this is effect of reservoir on the mechanical behavior of structure, and we need to include different physics of materials in the well, like a pore pressure, annular pressure buildup. We need to include plasticity. We need to include temperature dependency of materials, some creep phenomenons, or whatever you may name it. You know, there's a lot of physics that we need to take into account. But with this validated tool, we'll be able to say this is okay. This is when designed. This is good enough. Will it fail? Will it fail by collapse in such operation, or will it fail by fracture, tensile fracture in such operation, and how we can mitigate that? And by that we can come up with the alternative well design which is more robust and reliable in the future. Yes, I think I'm running out of time, so just to wrap up a little bit, what we hear is this, many have seen this as drilling, talking about drilling problems, and so I just lift it up a little bit perspective with respect to well integrity at high temperature. This is very challenging for us, and if we are not selecting good wells, design and good materials and good solutions, this can be tremendous problems. As maintenance cost is quite expensive. It's happened in IDTP2, so the well failed and this is stopped. No way to do the testing, also to perform production testing. So we need some novel drilling and well condition solution and well design are needed for such application. And our project Compass would provide a deeper insight into in the well physics at high temperature, and also there's some verified solution for sustainable energy harvesting. And last but not least, I think that this knowledge here can be transferred to ensure well integrity in other applications, especially in Taiwan, where we have a high temperature also, maybe not as high as this solution, but this is worth to look at, and also to increase the reliability of your future well. Thank you for your attention.